Good morning, everyone. We'll pick back up this morning in chapter 10. This slide here showing something we don't tend to test. It's in the book. I just wanted to make sure to mention how we can determine pressure, the pressure of a gas sample. More commonly today, we would just probably use a pressure gauge. So you use a calibrated gauge is the more common way. But the old-fashioned way is you would use a mercury column. So you could take a column of mercury, and what you would do is you would start with the mercury column at an equal height before you open the valve to the gas sample. And so then the moment you open the valve, one of three things could happen. The pressure of the gas could be at atmospheric pressure, in which case you'd see no change. So if the gas sample was just like at ordinary atmospheric pressure, then you'd see the height column stay the same, no change. And so that's one thing you can see. The second thing you can see is what we see in the first panel, which is the pressure of the gas is above atmospheric pressure. So here our gas pressure is greater than atmospheric pressure. We can see that because the gas sample has pressed the column downward on the side connected to the gas. And so that just means the pressure of the gas is greater than atmospheric pressure. And so then whatever the height differential ends up being, so if we take the difference of the height at the top versus the bottom of the column, and so we could work out the math here. It's just the 136.4 minus the 108 or 103.8. So that works out to be 32.6 millimeters is this difference here. And we're using mercury in this column, so that's why it's millimeters of mercury. And so if the atmospheric pressure, let's say the atmospheric pressure on a given day was 755 millimeters of mercury, that the pressure of our gas sample would be 755 millimeters of mercury, and then plus the 32.6 millimeters of mercury that it pressed the column downward. So the column has two pressures acting on it, the gas sample and the atmosphere. And so the gas sample is pressing down by a greater quantity. So that's showing that our gas sample is above atmospheric pressure. So just for this example, that would end up at a pressure of 788 millimeters of mercury. And then the other alternative is that when we open the valve to our gas sample, that if the gas is below room temperature, if the pressure of the gas is below atmospheric pressure, then the column of mercury will be pulled upwards because it doesn't have as much pressure pressing downward anymore, and the atmospheric pressure is pressing down by more. And so here we would just take the height differential. So the height differential here would be 52 centimeters. And so what we want to do in this case is to solve for our pressure of our gas is to take the atmospheric pressure and then minus the pressure of this height differential. Since we're below atmospheric pressure, we have to subtract. And so that would be 755 millimeters of mercury, our standard atmospheric pressure that day. And then we have to convert this to millimeters. It's centimeters of mercury right now. So that would be 520 millimeters of mercury. And so that'll take us down to 235 millimeters of mercury. Technically to 2 sig figs, but if you're tracking sig figs, the 52 only has 2. So we'd be at sig fig reminder here at 240 millimeters of mercury. So the key is that you could use this thing called a manometer to study the pressure of a gas sample. So like I said, we tend not to test this. I've seen manometer come up on Jeopardy a few times. I've had one student end up on Jeopardy so far, so you never know. One of you guys may end up on Jeopardy someday. And they may ask you, well, what's a manometer? Measures pressure of a gas sample. Barometer measures atmospheric pressure. So a few gas laws that talk about the relationships between the parameters of a gas. If you remember, the main thoughts of a gas sample are the pressure, volume, temperature, and quantity, usually in the moles. So let's look at the relationship between pressure and volume, and there's an inverse relationship. And this kind of makes sense. If you're imagining you have some sort of a piston, you have a gas sample, and you have a piston that you can move upward and downward, you probably know that if you press down on the piston on an enclosed gas sample, it's going to increase the pressure. So I think we know if we decrease the volume, that's going to lead to an increase in the pressure, and that's just the simple idea of an inverse relationship. And so if you have as you decrease the volume, you're going to increase the pressure. And so you can see that in either one of these two graphs where you have the decreasing volume, increasing pressure, or if you plot volume versus the inverse of pressure, then you get a straight line. And so that's just showing that you have an inverse relationship, that volume is inversely proportional to pressure. So if you either increase the volume, you decrease the pressure, or vice versa. So if you decrease the volume, then we're going to increase the pressure. So that's Boyle's law. Usually I don't think you see too often the names of memorizing which law is Boyle's law, but Boyle happened to study the relationship between volume and pressure, so that's why that's called Boyle's law. Charles studied the relationship between volume and temperature, and this relationship makes a fair bit of sense too. I would think that if you take a balloon and you warm it up, the balloon tends to expand under the increase of temperature, and then if you cool a balloon, if you pour ice over the balloon, sometimes you can pour like liquid nitrogen or something that really makes the balloon colder, it's going to shrink. And so that means that there's a direct relationship between volume and temperature. So as you increase the temperature, you're going to increase the volume of the balloon. And then likewise, if you decrease the temperature, you're going to decrease the volume. So we have this linear relationship. But then one of the things that happens is even if you flip the sign of temperature to negative on the degree C scale, that you don't like change the sign or relationship of temperature to negative. So we have to think about using an absolute temperature scale. And so the lowest temperature possible for any piece of matter would be 273.15 Kelvin. That's our absolute zero. And so we're going to see a lot of use of the Kelvin scale in this chapter. So negative 273.15 degrees C, not Kelvin. This degree C measure is equal to 0 Kelvin, the lowest possible temperature. So on an absolute temperature scale like Kelvin, it's not possible for a temperature to flip negative. So you'll see us use the Kelvin scale in this chapter so that we're not needing to change the sign of any quantity to negative. Like if you think about temperature dropping so low, it's not like the volume's going to turn negative. We have to think of, again, of using that absolute temperature scale, something like Kelvin. Let me come back for a second to talk about two relationships that we can make, one going back to Boyle's law and then looking at Charles' law here with volume directly proportional to temperature. One of those is, let's start with the PV relationship, that I can set P times V, and that would be equal to some sort of constant. So I'm just taking the relationship that pressure times the volume would be equal to some set of a constant values. This is meaning if you have a container that has a constant number of moles, a constant temperature, then the pressure volume would have a relationship. And what that means is that if you were to take the initial conditions of P1 times V1, so you have some container that has so much gas at a particular temperature, and you keep the amount of gas constant, you keep the temperature constant, then you, and let me even rewrite something here. Because I'm not trying to say it's the constant over NT, I'm just trying to say this is that constant N and T, so constant moles and temperature, that P1 times V1 is equal to a constant. Then if you change the pressure, you change the volume of that gas sample where N and T stay the same constant values that they have, then you can relate those to being equal to P2 times V2. So you can come up with this relationship that P1 V1 equals P2 V2, and that this works whenever you're at constant N, constant T for that change. So if the moles of gas of a gas sample are constant, the temperature is constant, and all you're changing is the pressure and the volume, then you can make a relationship that P1 V1 is equal to P2 V2. And we can make the same relationship with V and T, except that it's going to be V over T is equal to a set, something that's constant, as long as you're at constant pressure and volume. And so then you can relate V1 over T1 being equal to V2 over T2. And one thing here is that you got to use the Kelvin scale for your temperature. So you're going to have to, whenever you see a problem like this, you're going to generally need to flip your temperatures and always use the Kelvin scale and not the degree C scale. And again, this is at constant pressure and moles. So that's like the balloon in a confined space where the pressure is going to stay constant and the amount of gas in the balloon staying constant. We can come up with a relationship between V and T. And so let's see what problems we can solve with those. So let's look at a couple problems, in fact, equations. So we see the first problem here, we have a 2-liter gas sample, has a pressure of 2 atmospheres. What pressure would the sample have if the volume of the gas was reduced to 1 liter at constant temperature without any loss of gas sample? And so without any loss of gas sample, that just means constant moles. So the moles are constant, the temperature is constant. So this means we can use that pressure or volume relationship, that we can use the relationship P1, V1 is equal to P2 times V2. And so what we're trying to solve for is, what is P2 if we cut the volume from 2 liters to 1 liter? So this is going to probably increase the pressure, because we're thinking we're like pressing down on maybe some type of piston to decrease the volume. And that should lead to an increase in the pressure. Let's see if that's what we come up with. So our P2 should be equal to the initial pressure, initial volume, divide by V2. Then I'm going to plug in simply 2 ATM times 2 liters, and then divide that by the volume of 1 liter. And we come up with that pressure should be 4 atmospheres. So we cut the volume in half, we double the pressure. And so that, I think, makes good sense. And so again, this is just the picture of what we're doing here, just starting with 2 liters, and then we maybe have a piston that we can press down upon to cut the volume to 1 liter, and that pressure is doubling. And then the next problem is looking at a very similar problem, except where we have a container with a movable piston. The piston's going to just move to maintain atmospheric pressure. So if the container initially has a volume of 2 liters at 25 degrees C, what's the volume of the gas at 50 degrees C? Now this is where you're going to be careful to convert to Kelvin, because it seems like the temperature is doubling, but on an absolute scale, the temperature really isn't quite doubling. On the absolute scale, 25 degrees C is 298 Kelvin. And then on the absolute scale, because we're just adding 273.15, so 25 degrees C becomes 298 Kelvin. Adding 273 to 50, that would be 323 Kelvin. So our temperature is not quite doubling. We'd have to go to about 600 Kelvin to truly double the temperature of a gas sample. So if we want to compare the volume here, we use the Charles-Wall equation. V1 over T1 equals V2 over T2. And then what we're trying to solve for here is, what is the volume of the gas at 50 degrees C, assuming constant pressure, assuming an airtight container, that we're not losing any gas. And so our V2 should be equal to V1 times T2 divided by T1. So just solving this equation here for V2. So then and then also, if we think of increasing the temperature, should increase the volume. So if we're thinking of that direct relationship, we should be thinking that V2 should go up compared to V1. Hopefully if we make a mistake, we'll catch it, but we take our 2 liters initially, and then T1 was the 298 Kelvin, so T1's in the denominator, and then we're multiplying by T2, 323 Kelvin. Again, the key is we just had to know to go to the Kelvin scale here whenever we're dealing with problems in chapter 10. Almost, I can't think of any problem we're going to stay in degrees C in this chapter. So we got to go to the absolute temperature scale here. And so we do the math, 2 times 323 divided by 298. Shows that the volume goes up a little bit, goes up to 2.17 liters. If you didn't convert your temperature, you may have thought the volume would have doubled here, but it's not going to quite, it's not going to come even close to doubling. Okay, let's look at the relationship of volume and quantity. So one of the first observations made that really led in part to Avogadro's number and law being discovered is that if you took almost any gas sample and had 1 atmosphere of that gas sample at 0 degrees C. Now, for some reason, these two conditions here, they call that STP, standard temperature and pressure. I think they just do this to be confusing to you guys. The MCAT loves to test STP. I don't know why. They just, like, a lot of standardized exams love to use the fact that STP is 0 degrees C and try to catch you on it not being 25 degrees C. I don't think we go too crazy over this and make sure that you know that, but it's, 0 degrees C. So this is standard temp and pressure. And the key detail is it's not 25 degrees C. Everybody would think it's 25 degrees C, but it's 0 degrees C is standard temperature and pressure by the thing we call STP. But anyways, at STP, standard temperature and pressure, you have gas samples of helium, nitrogen, CH4. So obviously you have an atomic gas sample, a molecular gas sample, a molecular compound gas sample. And they all turn out to have the same volume. So the volume of those gases is almost irrelevant in terms of the composition of the gas. And then to have one other detail, though, is that you have 1 mole of each of those gases. So we have 1 mole, which is 4 grams of helium is a mole. The molar mass of nitrogen is 28.0, so that's 1 mole of N2. And we also have 1 mole of CH4. So if you have a mole of each of those gases in a container at 1 atmosphere at 0 degrees C, that they all turn out to have roughly the same volume as each other. And this graph here is showing you that there's a little bit of variation. The variation is coming from slight variations of breakdown of the ideal gas law. So some of the compounds are deviating a little bit, presumably because they're experiencing intermolecular forces. This isn't a very high pressure, so any deviations here, so maybe Cl2, which is a little bit further away than the others, is experiencing a stronger intermolecular force of attraction. But if you notice, most of those are in the 22.4 range. But the key is that gases have this relationship of 1 mole of any gas that behaves as an ideal gas at STP has a volume of about 22.4 liters. Now, another relationship could be that if we just put more gas into the container, and then, so if you said, well, what if we put more mass, more moles into the container? What's going to happen if we want to keep it at STP? If we want to keep it at 1 atmosphere at 0 degrees C, then the volume is going to have to expand. So we're going to have a larger volume if we put more quantity of gas into the container, so we get a direct relationship. And this should make sense. If you put more air into a balloon that can expand, it's going to expand to a larger volume and to maintain that same pressure and same temperature. Now, one of the things that we can do 2 things here. The first thing we'll do is show you the connection between all the laws that leads then to the ideal gas law. So we have a relationship from Boyle's law that V is inversely proportional to pressure, and then Charles and Avogadro's law show direct relationships between V and T, and then volume and quantity in terms of the number of moles. And so putting this all together would show that volume is directly proportional to N and T, and then divide by the pressure. So then if you were to do the kind of rearranging that we did before, you could write that pressure times volume directly proportional to N times T. You can then divide both sides by N times T and show that that's equal to a constant. And then that constant takes on a special name. We call that the ideal gas constant R. So the ideal gas constant R is equal to PV over NT. And so then this equation, once you see it, is how you can kind of go back to like the Boyle's law equation and say, oh, okay, this is why pressure volume was equal to the constant, and the constant would be nRT. So if we're at constant N, constant T, then that's how we're coming up with P1 V1 is equal to this. P2 V2 is also equal to the same nRT, so therefore they're equal to each other. So this is the same basic idea, or once you see the ideal gas law, you can kind of come back to those gas laws and derive those relationships very easily. You can come up with relationships that involve 3 of the parameters. You can say, well, what if we had a problem where we're at constant temperature, but PV and N were changing? So you can come up with a problem where you can take like PV over N, equal that to RT, where temperature is going to stay constant. We're going to change these variables from their initial values. They're going to be equal to RT, and then P2 V2 over N2 are going to be equal to the same gas constant at the same constant temperature. That's not changing. So therefore, P1 V1 over N1 is going to be equal to P2 V2 over N2. So if they're both equal to RT, then they're both equal to each other. So you can come up with a lot of relationships using the ideal gas law. We'll show you how to use an approach like that in a couple of problems. And then of course you have just the simple writing of the equation this way here. That's the ideal gas law. PIV-NERT sometimes is what we call that equation. But that's just the equation that relates whatever gas behaves ideally. So we say ideal gases obey this equation. And then generally, ideal gases are gases that, again, do not experience intermolecular forces and then occupy a negligible portion of their container. And so the main ideas of what makes an ideal gas are non-interacting particles, and negligible volumes. I don't think that's negligible. I need another G in there. So that just means that the particles aren't occupying much of the volume's container. So as long as your pressure is at a relatively high temperature relative to its boiling point, the closer you get to the vaporization point of a gas, the more the particles are going to be sticky and you're going to see a violation or a gas that doesn't quite obey the ideal gas law. And then also, whenever you have a really high pressure, you're going to see a breakdown in the ideal gas law because there's a lot of mass in the container that's occupying a then non-negligible volume of the container. Okay, so let's look at a couple of relationships here, or let's actually go through first and solve for the ideal gas constant. So let's take a look at R and see what it's equal to in numerical value. Now you may have seen R before. You might remember this number here. This is probably the units of R we use the most in a chapter like this, which is 0.08206 liter atmospheres per mole Kelvin. You may have also seen this number before. We use this number probably second most, the 8.314 joules per mole Kelvin. The cal per mole Kelvin, I don't think I've ever really used that number. So you see some other units here that we tend not to use that often. And then you can look at some other pressure units. But let's try to look at, well, where did these numbers come from? So how do we derive like the 0.08206 liter atmosphere per mole Kelvin? Well, it comes back to that ideal gas. So we go back to that 1 mole of an ideal gas occupies that volume of about 22.414 liters at STP. So that allows us to calculate R. So we just take, okay, well, we know that that pressure was about 1 atmosphere really precisely. It was a volume of 22.414 liters. And then so we're just plugging in that was 1 mole of gas at STP, 0 degrees C would be 273.15 Kelvin. So we throw all that into a calculator. So it should be the 22.414 divided by 273.15. That works out, and that gives me the 0.08206. And then the units just go liter atmosphere and then per mole Kelvin. And so with that unit of R, with the liter atmosphere per mole Kelvin, with these units here, this is really good anytime we have pressure in ATM, temperature we convert to Kelvin, moles, and then volume into liters. And so we can use that to solve problems that relate sort of ordinary units that we tend to see with pressure. I'll show you the derivation of this number later. We're not going to use this units of R until like the later part of chapter 10. So let's look at that constant later. And so primarily we're going to use this unit here for the most part within this chapter. And then like, let's say I give you a problem where pressure's in torr or millimeters of mercury. We now know those are the synonymous units. Well, instead of looking up this unit of R, why not just convert pressure to ATM and then use this unit of R? So usually we convert units so that we can use the 0.08206 liter atmosphere per mole Kelvin within problems so that we're not having to look up or know a bunch of different units for the ideal gas constant. Okay, and then we can also make a relationship with the ideal gas law going to PV is equal to nRT, our equation, and say, okay, well, let's start relating this like mass and molar mass. I know if I take mass divide by molar mass of a sample, that's just equal to moles. So if I take grams divide by grams per mole, that just works out to moles. So taking a mass of a sample, dividing by its molar mass allows me to relate to the number of moles. And so I could rewrite or plug that into my ideal gas law. So I'm just changing N to M over molar mass. And then I can do a few things from there. One, I can relate that to density because I see an M and a V here. If I divide both sides by volume, so if I rewrite this equation, divide both sides by volume, and then let me multiply both sides by RT to get rid of RT over here. Oh, I'm sorry, I want to divide both sides by RT. I'm making up math. Let me go back to this equation here and not screw my math up. So I want to divide both sides by RT. And then I want to multiply both sides by the molar mass to get rid of the molar mass. So then I can rewrite the equation now as density, which is m over v. So mass over volume is density. So density, which is mass over volume, is just equal to pressure times molar mass divided by RT. And so I just came up with a relationship using the ideal gas law, just simply taking note of mass and molar mass and rearranging the equation then to relate density to pressures, molar masses, ideal gas constant, and temperature. So the density of a gas sample is only dependent on the pressure and temperature and then what the gas is. So if I know what the compound is in the gas, or whatever makes up the gas, I can then solve for its density just knowing pressure and temperature. And then I can also do another thing, which is I can solve for molar mass. So sometimes we can use an ideal gas problem to determine the molar mass of an unknown sample. So we'll see problems that also relate to solving for molar mass. And so if I cross multiply molar mass, if I multiply both sides by molar mass to get rid of it over here, and then divide both sides by PV, I can write a relationship that molar mass is just equal to MRT over PV. And so then that gives me an equation. And if I need these equations, I'm probably going to derive them on the fly and not necessarily memorize them. But I can come up with a relationship then with my ideal gas law to solve for an unknown molar mass. So we'll see an example later that kind of says, okay, well, if I give you the mass of a gas sample, its temperature, its pressure, and volume, we should be able to work out what the molar mass of the sample is using the ideal gas law. So we'll come back and use these relationships within our next couple examples here. So let's take a look at a couple problems. And so first one, what is the pressure in ATM and torr? So let's calculate in two different units of 7.5 grams of CH4 methane in a particular vessel at 23 degrees C. And so I have pressure, volume, temperature, and I'm calculating, I want to calculate pressure, and I have mass where I could get molar mass and therefore get moles. So I can come up with a relationship here between PV is equal to nRT, and I'm probably going m over molar mass times RT. Since I have a mass here, I can look up or determine the molar mass of CH4 and plug it into the problem. And then I want to solve for pressure, so I'll divide both sides by volume. And so I should be able to plug in accordingly. Now I could have done a few other things. I could have just solved for the moles on the side and then plugged straight into here. Yeah, so that's an option too. So I could just have solved for the moles of the gas and just plug into PV is equal to nRT. Or I could rewrite m over molar mass and just do it in one step. And so if I'm going to do it in one step, I have 7.50 grams. This is a great chapter for writing in units. If you don't write units in, you will probably accidentally make some mistakes in this chapter. So if we're just being mindful of our units, we'll catch a lot of mistakes. We'll make sure that things are in the proper unit and hopefully minimize just simple conversion errors. So obviously I don't want to leave this 23 degrees C because degree C doesn't cancel into Kelvin, but if I didn't write per mole Kelvin, maybe I make a mistake and leave this in degree C. So I want to convert this to Kelvin. So that'll be 296 Kelvin. And then I want to divide that by molar mass. Molar mass of CH4, 1.008 times 4 plus 12.01, 16.04 grams per mole. And then the volume, 2.50 liters. And so hopefully most of my units are canceling. Let me do this different color. So grams are canceling, liters canceling, Kelvin's canceling, and then the 1 over mole flips up to mole, so the mole divide by moles canceling. And then the only unit not canceling here is atmospheres, which is good because that's what I'm looking for, is my pressure to be calculated in ATM. So I get 4.54 atmospheres. Now the problem asks for the pressure in ATM and torr. So we could go through this problem with the torr units like on the previous page and then solve it again, but the easier thing to do is just simply convert this to torr or to millimeters of mercury, same unit. So 1 ATM, 760 torr. And so just multiplying by 760, that's an exact conversion too. So we're not going to round this to 2 sig figs, but that gives me 3,450 torr. So millimeters of mercury, or the synonymous unit of torr, really high pressure in that unit. Now, what's the density of the gas? Well, there's 2 ways to solve for the density of the gas sample above, or maybe even more than 2, but there's 2 ways I can think of. One is probably the more complicated way, but if you were thinking of the equation I wrote earlier, or you're able to derive back to this equation, we could use this equation. We know the pressure, we know the molar mass, we know R and T. So let's drill this in real quick. We'll use the pressure we calculated here, 4.54 atmospheres. Multiply by 16.04 grams per mole, RT 0.08206 liter atmospheres per mole Kelvin. We haven't changed the temperature because it said what's the temperature of that gas sample, so under the same conditions as above. So we're still at 296 Kelvin. I get 3.00. Now let me think of the units to make sure everything works, but my ATM cancels, the Kelvin cancels, the 1 over mole flips up to cancel into the per mole, and what I'm left with is grams per liter. So it's good to get the units of density out and then to make sure you see what the units are through the problem. If we got some other units, maybe we made a mistake and divided by something we should have multiplied by, or who knows. So checking our units is a really good idea here in this chapter. Now, is anybody thinking there's a simpler way to find the density of that gas sample? Was anybody saying there's actually a much simpler way? Well, in the above problem, we told you how much mass there was, 7.50 grams, and we told you the volume of the vessel. So you may have been saying, well, why don't you just take density is that 7.50 gram sample over the 2.5 liter vessel. And of course, that's 3.00 grams per liter as well. And so there's 2 different ways for this particular problem that you could have solved for the density. So density is just mass over volume. It could fall out from the ideal gas law, and it just has its basic relationship of being a ratio of mass to volume. Now, if we, this gas sample is at a higher temperature than STP, it's higher than 0, and it's at a higher pressure. It's at 4.54 ATM, and we had 2.5 liters. What do you think the density would be? Do you think if we went to STP, so drastically lower the temperature, well, not drastically lower the temperature, drastically lower the pressure, and then slightly lower the temperature. Do you think that would cause the density to go up or go down compared to the density of 3.00 grams per liter? Density should probably drop because we have to reduce the pressure, so we're gonna have to allow the gas to expand to get to that STP. So to get to a pressure of 1 ATM and to lower the temperature, we're going to have the volume go up by quite a bit, and that's going to lower the density of this gas sample. So the density at STP, and again, remembering that 0 degrees C, so our density here would be calculated from pressure times molar mass over RT. And so in this problem here, we're just plugging in the pressure precisely of 1 atm. STP means like precisely 1 atm, so it's like 1 with an infinite number of zeros in terms of sig figs. So it's an infinite number of sig figs here, and then times the molar mass, 16.04 grams per mole, and then dividing that by the ideal gas constant, which is technically rounded to 4, just like our molar mass. So we're going to determine this just to 4 sig figs here. We could determine this to more sig figs if we wanted to. And obviously we can't divide by 0. Like if we plug in 0 degrees C, we're going to get an undefined number. We just have to go to Kelvin. So it's 273.15 precise Kelvin for 0 degrees C at STP. So 16.04, divide by our gas constant, divide by 273.15. I get a lower density here, 0.7156. And again, let's check our units. ATM cancels, the per mole cancels, our Kelvin cancels, and we only have grams per liter left, which is good because that's our density unit. So again, our density lowered because we had to expand this gas in order to achieve this lower pressure. Okay, so what about generating gas from some type of chemical reaction? And so let's say we have the reaction of sodium azide being decomposed in order to fill an airbag. And so we had talked about this reaction back in chapter 3 as an example of a decomposition reaction. And so the decomposition is sodium, this is called the azide ion. That compound as a solid decomposes to give sodium solid and then plus nitrogen gas. And then if you have this reaction take place in a way that it can spontaneously take place, say when there's a collision in a car, you can use the gas of nitrogen to fill an airbag. And this was a mechanism that was used in older cars. I don't think it's used today all that frequently. Unfortunately, I think we mentioned this earlier, that a lot of times sodium flies with the nitrogen and then that causes burns. It usually burns the airbag and can burn the person. So usually these days, like charged packs of CO2 are used and it's not an interesting chemistry problem. But you could ask the question, how much of the sodium azide do you have to have decomposed to fill a 50-liter airbag with 1.25 atms of nitrogen at 22 degrees C, and it's going to use this reaction to produce the nitrogen. And so the idea of this problem is that we're going to relate, like, how much nitrogen do we need to fill the airbag? So we're going to look at our initial conditions and kind of use the ideal gas law to say, well, how many moles of nitrogen do we need there to be to fill the airbag with that gas? So we're going to solve with our ideal gas law the gas moles that we need to be in that airbag. And then we're going to use stoichiometry to say, if I need that many moles to be produced by a reaction, we're just going to then use a stoichiometry problem to go to moles of sodium azide and then the mass of the NaN3. So it's just saying we have a reaction that's going to generate a gas. How much gas do we need there to be? Well, by the ideal gas law, I know the pressure, I know the volume, and I know the temperature. So I can solve for moles. And so I'm going to solve for moles here. Let me write this over here. My moles of N2, they're going to fill that airbag, should be equal to PV over RT. And so we take the pressure, 1.25 atmospheres, multiply it by the volume, so we need to fill up a 50-liter airbag. I'm going to divide by our gas constant. And then 22.0 plus 273.15. So that'll equal 295.15 Kelvin. So let's do the math. 1.25 times 50 divided by 0.08206 divided by 2.95.15. So I get that we're going to need about 2.5 moles of nitrogen to fill that airbag in order to have that particular pressure and volume at that particular temperature. Now let's again double check our units. Atmospheres cancel, liters cancel, Kelvin cancels, and then 1 over mole flips up to be moles. And so that's how we're getting moles out of this equation. So 1 over moles in the denominator flips up to moles in the numerator. And so how much of this needs to decompose in order to produce 2.58 moles? Well, if 2 moles decompose, I get 3 moles of nitrogen. So do you see how it's going to be slightly less than 2 moles of sodium azide? Just if I need 2 moles of sodium azide to decompose, give me 3 moles of N2, but I really only need 2.58 moles of N2. It should be a little less than 2. Let's work out using stoichiometry. So we're going back to just a little review of stoichiometry. The number of grams of sodium azide that we need here should be able to be calculated from the 2.58 moles of N2 that we need to produce. Now for every 3 moles of N2 that are produced by this reaction means 2 moles of NaN3 had to decompose. And then I just need to use the molar mass of NaN3. So it's 23.00. Or technically it's 22.99. I don't know why I like to use 4 sig figs. I mean, if you are rounding, it's probably not the end of the world. 14.01 for nitrogen times 3, that's 65.02. So 1 mole of NaN3 is 65.02 grams. And so we're just going from moles of nitrogen to moles of sodium azide, and then moles of sodium azide to its mass. So 1.72 moles of sodium azide times 65.02. That's 111.8 grams. Call that 112 grams. So this relationship here is just how we can relate a chemical reaction taking place to generate a gas to then figure out how much of the reaction we need to have take place to generate that particular quantity. So this is just generating gas from chemical reactions and then solving a stoichiometry problem along the way. So we're just using our gas data to relate to moles. Just remember that your gas data always relates to the moles of your gas. We can't directly relate the gas data to the moles of sodium azide because it's a solid. It doesn't obey the ideal gas law because it's not a gas. So we have to relate the gas in the problem to the ideal gas law and then use stoichiometry to get back to the starting material. Let's take a look at partial pressures. So partial pressures are where we have 2 or more gases in a container. Could be air, and the container is the atmosphere, and we have the partial pressure due to oxygen and nitrogen adding together. So we could think of a gas mixture that we encounter often like air, but any gas mixture, the gases act as if the other gases they're all non-interacting particles. So if we have 2 gases in a container, their masses, or their pressures just sum together. So if I have a container that has like 2 atmospheres of say oxygen, O2, and I have 2 atmospheres of N2 nitrogen, then I'm going to have 4 total atmospheres. I'm just going to sum those pressures together, and it doesn't quite matter what the gases are. They just sum up to be the total pressure by taking the sum of the individual partial pressures. And so if we have a gas mixture, we call these partial pressures. So P1 would be the partial pressure of component 1, P2 the partial pressure of component 2, and those are just the pressures those gases would have if the other gases weren't even in the container. So each of those pressures is just dependent on PV is equal to nRT. So like P1 is just dependent on N1, like it's just dependent on how many moles of that component there are. P2 is just dependent on N2 times RT divided by V. And P1 and P2 are in the same container, so they're at the same temperature, at the same volume, so they tend to have the same temperature and volume. So I'm not writing the subscripts in for temperature and volume because the two gases are at the same temperature, at the same volume, so they have the same volume and temperature as each other because they're in the same container. So let's take a look at a little bit of math that you can do with gas mixers and take advantage of that sort of idea that pressure 1, the component 1, is just related to N1 RT over V. Well, we can relate that to the total pressure. The total pressure would just be, well, how many total moles are there of gas inside the container? And then that relates to RT over V, just like P1 related to N1 RT over V. So the total pressure relates to T over V. There's no T1 V1 here because, or T2 or V2, because component 1, component 2, component 3, et cetera, are all in the same container at the same temperature at the same volume. Now, what this then leads to is because the gases are at the same temperature and volume and the gas constant's the same, it reduces P1 over P1 over the total pressure to be equal to N1 over the total number of moles. And so N1 over NT, that's also a value that we denote by a value that we call the mole fraction. So the mole fraction of 1, this is just the symbol for mole fraction, is just equal to the moles of component 1 divided by the total moles. So our mole fraction is just what's the fraction of one of the components divided by the total. And so our X1, they usually italicize it, is moles of component 1 over the total moles. And so N1 over NT descriptively. And so then what we can come up with is if you call this here mole fraction of component 1, then you can relate the mole fraction of component 1 to the total pressure. So the partial pressure of component 1 is just the mole fraction of that component times the total pressure. And so this is just another way of writing that this is N1 over NT times PT. So it's a fair bit of writing, but it's just, this is Dalton's law of partial pressures, that the partial pressure of a component is just its mole fraction times the total pressure. And then its mole fraction in terms of descriptiveness is just N1 over NT. So it's just a simple rewriting of this equation here into this form here, taking note of what the mole fraction means. Let's take a look at a problem we can solve with this. So let's say we have a gas mixture, 5 grams of helium, 5 grams of oxygen in a 15-liter vessel. What's the total pressure? So there's two basic approaches here at this problem. I could calculate the partial pressure of each component and then simply sum them together. So the total pressure should just be equal to the partial pressure of helium plus the partial pressure of oxygen. And then these two pressures are just the pressures they would have as if the other wasn't even there. So like the partial pressure of helium would just be equal to the helium pressure, so 5.00 grams divided by 4.003 grams per mole, the molar mass, times RT. (298 Kelvin). And so we're also starting with the idea that P1 is equal to N1 RT over V. So just like the equation I'm plugging into here was just to take N1, so this is my N1, and then times R times T, and then I need to divide all this by the volume, 15.0 liters. And so liters cancels, Kelvin cancels, grams cancel, per mole cancels. The only thing not canceling is ATM, the pressure. So the partial pressure of helium in that container, I have a little over a mole, so it's going to be probably a pretty high pressure. So it's 2.02 ATM. So just a simple pressure calculation as if the other component wasn't there. And then the same thing for the oxygen. So now we just have a lower number of moles, so that's our moles times R So it should be a lower pressure because we have much fewer moles. So I get 0.255 ATM, and again, the same cancellation as above. So everything's canceling except for the ATM. And then all I need to do is sum these two up to get my total pressure. So my total pressure here would be 2.02 added to that pressure. So that's 2.27. So I'm just adding the two partial pressures up to get the total pressure. Now, I could have done this other ways. I could have summed up the number of moles and got NT and taken NT times RT and total times RT. So I could have said, well, my total pressure would just be the total moles times RT over V, and then just solve for NT and plug directly and done this problem once. That would be fine. That should get me the exact same answer. The relationship between mole fraction doesn't really come into play so much in this problem, but the mole fractions, if we wanted to go to the mole fractions, we could relate them to the total pressure to the individual moles. So I don't really need to use the mole fraction here, but I probably could have come up with a way using mole fraction to maybe a third way come up with a solution to this problem that probably would have taken a little bit more writing, a little bit more work. Let's take a glance at this problem here. I don't think we're going to be able to solve it, but I think it would be good to think about this problem twice anyways. But the problem here shows us a technique that we can use to determine the molar mass of a gas sample. So the way this works is you take a bulb. This is just a bulb that has a little opening to the atmosphere. So, and it's called a Dumas bulb. And sometimes we do this in lab. I don't know if we're doing this experiment this semester, but what you do is you figure out the volume of the vessel. So the first part of the lab is usually filling the thing with water, getting the mass, dumping out all the water, drying it really good, getting the mass of the empty container. So you can figure out precisely how much water was in the container, from which you can then determine the volume of the bulb. And so you're usually trying to come up with an estimate of what's the volume of the bulb. And so that's given to us here. You're then trying to figure out what was atmospheric pressure. So you have to have like a barometer so you can know the pressure on the day of the lab. And then you put some liquid into this container, and then you boil off all the liquid until you see all the liquid's gone. And so you vaporize all the liquid until it leaves the bulb. And then the only pressure inside of that bulb should be the gaseous molecules of the sample that had vaporized. And then after the experiment's over, you just cool down the container, and then that gas condenses because you go back to a lower temperature, and then you liquefy the gas, compare the mass before and after, and from that you should be able to work out what the molar mass of the gas is. So we'll start with that problem on Monday. So let's just end today with our quiz, and then get into the weekend, and we'll start with that problem next time. Best name today, Heisenberg. Breaking Bad. Let's go. All right, I'll see you guys on Monday. Have a great weekend. Welcome. Have a good weekend. Hi.
Last chapters, I understand the orbitals are balanced electrons here. Why for lithium right here it's like 6, which is like the total?
For some reason, this diagram, they like to show the 1s and the 2s. And if you imagine this not being shown, then it would just be then kind of like, if you scroll later where I have, like this diagram here is just kind of showing us the 2s. And so the first diagram is showing you the 1s and the 2s. And for reasons that they don't need to. Like they just, the diagram showed them. So if I could have just cropped it out, I could have. And so, but this is trying to show you, the idea I think what that picture is getting at is the 1s orbitals are here, so they're not going to overlap as much. The 2s are bigger, so they're going to overlap and go up and down by more. Okay. And so then when we get to the rest of the second row, we assume that the core orbitals aren't really participating in bonding. You know, so the core orbitals are just doing their thing and not really going up and down. Or if they are, it's very, very small contributions.
But mostly it's the valence electrons.
Yeah, exactly. Yeah.